Hi everyone and welcome to NMC1. Today we'll be looking at a type of failure called fracture toughness and the related theory behind it. So you know that in chapter 6 what was done was the mechanical properties of materials, and we found that materials can either be brittle or ductile. Now in fracture mechanics, or determining a fracture toughness of a material, you'd have to know the type of failure, and the physical representation of these two types of failure can be schematically represented as follows. You find that now you have a brittle failure. It's like glass. When you break a glass, you find that the two surfaces are relatively flat. So this would be a type of failure which is a brittle failure, and a ductile failure would look something like this. You have two samples, and you have sort of like a dink on this one. This is how basically the two surfaces would look, because the ductile material undergoes more plastic deformation than a brittle material. So basically, fracture mechanics, it relates the material's properties, stress levels, and size of crack producing flaws. Crack producing flaws are like sharp edges inside the material, because we know that there's no material that's perfect. So internally, for example, during a steel making process, there's going to be some voids inside the steel. It may be micro voids or it may be macro voids, but there will always be voids, and those voids, those edges within the steel, creates a level of stress concentration. So you might find that the material has an internal crack, like the one being represented here is an internal crack, right? Now around the crack there is a specific stress concentration. So there's a higher stress concentration around the crack, and as you go away from the crack, the stress concentration becomes a bit lower. This is something that if you imagine that when you have a wound on your hand, right, and then somebody is busy touching your hand, moving towards the wound with the same amount of force, you'd find that with that same amount of force, as they approach the wound, it actually becomes painful. It's because the wound has stress razors, like the pain. That's where the pain is coming from. It has stress razors. So even though the force of the pricking on your hand is the same towards the wound, but the wound is actually an area that has a high concentration of stress razors. That may be the defected wound that is causing the pain. So the same way with the material, what you have is that with these cracks, there's a higher concentration of stress, localized stress, or where you have a crack. But the cracks can either be a surface crack or internal crack, depending on the specific forming of the material. So what we know here is, if you look at the subsequent drawing on the left, this is a representation of a crack, but this is an external crack, a surface crack, and then you have a specific force that is being applied to the specific specimen, right? Say the force, the working stress that you're applying on both sides, right? Now once you get to the tip of the crack, once you get to this zone, what happens is that because you're actually at this tip, and this tip is a sharp edge, it has stress razors. So meaning that the working stress is amplified. So you have a localized stress. So the stress that is actually being exerted here is the working stress plus the localized stress that is actually being facilitated by the stress intensity that comes with the sharp edge, right? As you can see from the schematic, initially when you're far away from the radius of the crack, you'd find that the only stress that is felt within the material is the remote stress or the working stress. So the closer you get to the origin of the crack, you start having a localized stress increasing. Just think of the analogy that I used of a wounded hand. That's basically it. So with fracture mechanics, we want to understand what the stress intensity is actually doing to facilitate the material to be able to fracture. Now there's a formula associated with this. That's the K1 formula, right? K1 formula, it's the working stress multiplied by a constant root pi multiplied by the crack size. Now K1 is the stress intensity, and then to measure the fracture toughness of a material, there's a critical stress intensity, which is called the K1C value. So the K1C value just actually represents the stress intensity that will result in the material to fracture. This would basically be, it could be at a specific working stress, right? And it has a specific critical crack length. This is when the material will actually start to fracture or fracture. So, but the one in the K1 or the K1C is represented by plane strain. This type of mode is mode 1, which is the plane strain mode. Now this is the orientation of the forces being applied on the specific material. There are other modes. There's K2C and then there's K3C, but for this case we're only focusing on K1. So you would have the force being applied upwards and down here. This is mode 1. That's why this is called the K1C or the K1, which is the stress intensity. So basically that's it. Another theoretical concept that you need to understand is you could be asked why the material that is ductile, actually the crack propagation, for the crack to propagate, it takes, you know, a bit more time than when it's a brittle material. The basic answer is, or the basic backing of that theory to answer that, is the fact that with a ductile material it has a plastic zone, right? So this plastic zone has a counteractive stress or energy that counteracts the applied stress or even the stress raisers. So it's actually acting against the stress raisers to reduce the amount of stress intensity at the crack tip. Whereas with a brittle material, you don't have this plastic zone. So what you'll just have is it will just be this. Say you have a surface crack and there's no plastic zone, meaning that by the time you get the force acts on this sharp point, there is a lot of stress raisers here in terms of the intensity. So because there's no counteracting force or counteracting energy from the plastic zone, the material easily just breaks. it doesn't undergo what is called plastic yielding. Now the cracks, as mentioned earlier, there's an internal crack. An internal crack is actually 2A. You can see here only a half of that crack is actually been labeled as A. So the entire internal crack is 2A, and then the external crack or the surface crack, it's literally just A. So when you do calculations and they've given you the internal crack and they say that the crack length A is, or the internal crack is this much, you must just know that you have to divide that by 2, because that will be 2A. So now let's move on to impact testing. Impact testing is a testing method that is used to test the toughness of a material. Basically, how they arrived at this testing method is actually being used to test the toughness of a material. Basically, toughness is the amount of energy a material is able to absorb before it fractures. That's the total amount of energy that a material absorbs. If you look at the stress strain curve, this will be the stress, this is the strain. You'd have the, let's choose a ductile type of profile. The area underneath this entire curve is actually the toughness of the material. Basically, how much energy is the material able to absorb before it fractures. Remember, this is different from the modulus of resilience, because the modulus of resilience is just the area under the elastic zone, but the entire area is actually used as a measure of the toughness. So the Chappie ISO test was invented. This is the Chappie. The one that's used mostly is the V-notch. Chappie V-notch type of impact testing. The material is orientated in this way, and then it's fixed to this base, and then there's a hammer. You see it faces the macro crack or V that has been made on the material faces in the other direction, and then there's a pendulum that swings and it hits the material and it breaks it, and it would actually afterwards, after impact, obviously the pendulum would not go to the same height after the impact, so it would be at a specific height, right? So that specific energy, when you know that the potential energy of a material is mgh, so they use the difference in the height to be able to determine how much energy the material was able to absorb. That way they would know the toughness of the material, so you'd know. But the reason you do this Chappie test is to see once you start plotting it against temperature, because different materials behave differently under specific temperatures. For example, probably most of you know the movie Titanic, or the actual Titanic, which was the ship. What has happened is that the steel that was used to design the bottom part of the ship was tested under ambient temperatures. So now the engineers that did that did not accommodate the fact that the water may be cold. So that's why when it hit an iceberg, that bottom part actually broke in a brittle manner, right? It may have been ductile when it was at ambient temperatures, but when it goes to be somewhere near 0 degrees Celsius, the material had become brittle. So that's actually when these kind of discoveries were made, that the material have to be looked at how they behave under different temperature conditions, because they don't behave the same. The fact that a material is ductile in a specific temperature range doesn't mean that it's going to be ductile below a certain temperature range. So material had to be tested for their usability under specific conditions. So it brings us to what is called the brittle to ductile transition temperature. Basically, what the brittle to ductile transition temperature is a specific temperature, right, where the material, at that specific temperature, the material is either becoming ductile or brittle. That's the transition temperature, right? And it is at a specific impact energy. Sometimes it may be, for example, a 30 joules of impact energy. But usually the mild steel, it's the one that actually has this flexibility to move from ductile to brittle state. But for most FCC steels, you find that the steel is actually, especially low strength material like copper, is always ductile irrespective of the temperature. Once you decrease the temperature to 0 degrees, it still remains ductile. Also aluminium as well, it's one of those materials. And you have some which are high strength steels. Even at higher temperatures, there's no transition to a ductile state. They remain brittle because they are so hard. So this is actually what you have to know about the impact testing, and you must understand what the ductile to brittle transition temperature is. And also, in different materials, you may find that they've been alloyed with different amounts of interstitial components, and that also affects the ductile to brittle transition temperatures. And you'll see the behavior being profiled according to the strengthening mechanism of the specific material. So now we'll do the questions that relate to fracture toughness. We'll see you in the next video.